Go ahead.
Thank you very much. Hello, everyone. Can you hear me?
Yes.
Thanks. I am Kenta Ochi, visiting scientist at ECMWF, seconded from Japan Meteorological Agency. I am working on snow data assimilation at ECMWF. Thank you very much for this opportunity to talk at ISDA online. Today, I will talk about recent activities on snow data assimilation at ECMWF. First of all, I would like to talk briefly why land surface matters as an introduction. Next, I will talk about current land data assimilation system at ECMWF with the concept of coupled data assimilation. Then, I will move on to recent activities on snow data assimilation for both numerical weather prediction and reanalysis. Finally, I will sum up my presentation with summary and future plans. To begin with, left figure shows the global mean energy budget, including land and ocean. Focusing on the surface, incoming solar radiation and back radiation from the atmosphere are absorbed by the surface. On the other hand, the surface emits long-wave radiation to the atmosphere, and part of incoming solar radiation is reflected to the atmosphere. In addition, thermals and evapotranspirations are transferred to the atmosphere through sensible and latent heat flux. As described here, land and atmosphere interact with each other. The amount of interaction is widely different depending on the land surface status, as albedo on snow, described right figure. So it is important to represent the land surface status appropriately. Land data assimilation makes it possible to represent it more appropriately by using observations. Next, this diagram indicates brief outline of current land data assimilation system at ECMWF, including the relationship with atmospheric analysis. In the system, first guess is calculated by coupled model. Atmospheric dA and land dA run separately, and increments are calculated for each component. The increments are added to the first guess, and this is used as initial conditions for next cycle. This means weakly coupled data assimilation system. In this way, the effect of interaction between land and atmosphere is considered. It enables to propagate the impact to the other Earth system component. The LDAS includes two-dimensional optimal interpolation for screen level temperature and relative humidity, 2DOI for snow depth, SEKF for soil moisture, and 1DOI for soil and snow temperature. The increment of each component also calculated separately. Today, I will focus on snow depth analysis by 2DOI. The snow model is a component of land surface model at ECMWF. The current operational snow model consists of single-layer snowpack and predicts snow water equivalent and snow density. Instead, snow depth observations from SYNOP and national networks are used in snow data assimilation. In addition, IMS snow cover product is also used. It is binary information made from satellite observations. IMS is used in the data assimilation after converting from binary information to snow depth. It can be available at 23 UTC and assimilated on the next day at 0 UTC. The data assimilation is based on 2D OI. The increment spread isotropically by the horizontal structure function used for background error covariance. This slide is an example of in-situ observations and IMS. Snow depth reports are available on the GTS. They are increasing in recent years, including 0 centimeter reports, which are crucial to remove excessive snow by the model. However, there are still sparse regions. For example, in the US, IMS snow cover plays an important role in such regions. In the operational system, latest observations can be reflected in the analysis. In addition, they reduce systematic biases by the model. The top left figure shows snow depth analyzed without observations, and the right figure shows analysis using observations. The bottom left figure shows the differences between them. Almost all regions have negative values in the figure. It means excessive snow is removed by data assimilation in many cases. In this way, snow depth is modified by snow DA, and it improves forecast, especially in the lower atmosphere. Next, I will move on to recent activities on snow data assimilation. This slide shows the impact assimilating IMS over the Tibetan Plateau. In the current operational system at ECMWF, IMS has not been assimilated on mountains over 1,500 meters. But this results in excessive snow on the Tibetan Plateau in Era 5 and control experiment at the bottom left figure. Red line and blue line correspond to in-situ observations on the Tibetan Plateau and the experiment assimilating IMS respectively. You can see it is improved by assimilating IMS. It also improves forecast scale in the troposphere during winter season, like the bottom right figure. We are testing the impact on the other seasons. Next two slides relate to quality control of snow observations. Real-time or near real-time monitoring is important for operational system, not to include inappropriate observations in the data assimilation. Regarding IMS, fresh snow has been sometimes removed by assimilating IMS. IMS is assimilated on the next day, so latest observations are not included in the assimilated IMS when assimilated. The top left figure shows less snow than the right figure. This is because the IMS in the bottom left figure is assimilated in the analysis. This situation is improved like the top right figure by rejecting IMS if much fresh snow exists in first case. Regarding SYNOP observations, suspicious 0 centimeter reports have been assimilated in China, except 0 UTC, since 2019. This is improved by rejecting suspicious reports except 0 UTC. Top figures show the impact rejecting the reports. Snow depth is much reduced in the current system, but it is improved like the right figure. These two QC modifications will be implemented into the operational system in the near future. This slide shows recent activities on reanalysis. There are some issues with the latest reanalysis at ECMWF ERA 5. Regarding observations used in ERA 5, IMS has been assimilated since 2004. This resulted in inconsistency around 2004. Bottom figure shows time series of snow water equivalent in ERA 5. Each line corresponds to each year from September. IMS is assimilated only after 2004, so there is inconsistency between before and after 2004, corresponding to blue and red line in the figure. It is important for the analysis to be consistent for longer period, so necessary to be improved. In order to improve it, we tried to use ESA CCI SYNOP. One of ESA CCI SYNOP cover product based on AVHRR starts from 1982, covering longer period than IMS. As a first step, we tested the impact to assimilate ESA CCI SYNOP cover by offline land data assimilation system. This includes only land forecast and land data assimilation hosted by ERA 5, so much cheaper and faster to run than coupled system. The bottom figure is the same as the previous slide, but based on offline analysis using ESA CCI SYNOP cover. It is more consistent around 2004 than ERA 5. We will test it by coupled system for next reanalysis. This is summary of my presentation. The current ECMWF LDAS relies on weakly coupled DA approaches. It includes snow data assimilation, and it plays an important role in the ECMWF system. For example, systematic snow depth biases are reduced, and it improves forecast scale, especially in the lower atmosphere. And I introduced several ongoing activities: IMS assimilation over the Tibetan Plateau, QC modifications, and ESA CCI SYNOP assimilation. These activities are important for both numerical weather prediction and reanalysis. To end my presentation, I will talk about future plans at ECMWF. I said our LDAS includes several analyses for each component. In order to enhance consistency with each other, it would be better to be analyzed by unified method. We are considering to move to unified multivariate ensemble-based LDAS. As a first step, we will start with extension of the SEKF to include all components for land. Using ADA information can make it possible to consider flow dependency in the LDAS, and it would improve the analysis. Towards stronger coupled assimilation, we will also start to develop outer loop coupling. Coupling through the observations operator will be also important. It relates to the Future Copernicus Satellite Mission, CIMR. The future mission would be crucial for further development of this approach. Altitude simulation using CMM emissivity on snow-covered area was also tested at ECMWF. Through these future activities, we will develop random data assimilation system for entropy and reanalysis. That's all. Thank you very much for your attention.
Thank you for that very nice talk. We do have some questions already in the YoPad. So Gabrielle Delanoy asks, how exactly is IMS currently assimilated? What technique? And how are uncertainties on IMS set?
The IMS is converted from binary information to SNO depths depending on the status of IMS, snow free or snow covered, and the status of first guess. The observation error set to twice as the time of observation.
Okay, yeah, thank you. And Rolf asks, thanks, great talk. Does ESA CCI assimilation result in a bias with respect to IMS assimilation?
The biases by model is also reduced by ESA CCI assimilation. And I compared ESA CCI assimilation and IMS assimilation in recent years, and the biases in the northern hemisphere is almost the same with the IMS assimilation.
Interesting. We have more questions for you. So from the chat, hi Kenta, thanks for the talk. Do you assimilate satellite data for SNO DA? If so, what types of satellite data are assimilated? L1 or L2 satellite product? Thanks, Swapan.
We use IMS. In IMS, many satellite observations are used and merged. So L1 or L2 satellite product is not used in our analysis.
And then from Clara Draper, is there a reason that you are using ESA CCI instead of the coarser resolution IMS data before 2004? Great talk.
I think there is coastal resolution IMS before 2004, but it covers not so long period than ESA CCI SNO cover. So I think it might be better to use ESA CCI SNO cover for 1980s or early period before 2000.
Clara, I think, is writing a response. Thanks, IMS stops in 1992, I think. She writes.
Oh, thank you for your comment.
Okay. And this is a question by Jairu. How do you handle the latency when using IMS snow cover data?
IMS snow cover is only assimilated at 0 UTC once a day. And SYNOP observation is 4 times a day. So the latency is a bit different from between instrument observations and IMS.
So the IMS is only assimilated at that time.
Yes.
It's recorded or available.
Yes, exactly.
Okay. Thank you very much. I think that's the end of our questions. So thank you very much, and let's thank our speaker.